Here's a question for you. If I give you 500 consecutive digits of either e or pi, can you tell me whether they belong to e or pi without checking? Let's say I give you the following 500 digits. These are 500 digits starting from the 800,000th place of pi, or e. Can you tell me, using some property of either pi or e, which one this sequence belonged to? I couldn't find the answer online, so I tried my own thing. So here was my idea. Let's study the distance between repeating digits in two transcendental numbers, pi and e. In particular, let's look at the digits that constitute them. These digits range from 0 to 9. Since there are an infinite amount of numbers that follow no pattern, it follows logically that each number is repeated an infinite amount of times. What I seek to find is a characteristic pattern in the gaps between repeating digits that will allow me to know, given any 500 consecutive digits, whether they belong to pi or e. The layout of this video will be the following. First, we will go through the code that I wrote. Then I will talk about the results of the statistical analysis that I ran as a part of the code. I will show both graphs and tables. Then, finally, I will discuss the conclusions that we can draw and determine whether it's possible to determine whether these 500 digits belong to e or pi, and if so, how. Without further ado, let's dive into the code. This code, written in MATLAB because I find it intuitive and have access to it as a college student, starts off with a list of the first digits of both pi and e. You can see them here. I got all of the way to 500,000 digits. Anything beyond that is beyond the capabilities of my laptop, and these 500,000 digits was enough to see the converging data. The heart and soul of this code is a function that I made. This function takes any array of numbers and spits out the amount of digits between that digit and the next time that digit is repeated. For example, if we take pi and look at the first number of the output function, it is 9. That means that the ninth digit after the first number is the same as that first number. A few final numbers are filled with zeros as the numbers stop repeating as they run out. Since pi and e are transcendental, we can ignore these zeros. Alright, let's discuss results. These graphs that I will show you have the x-axis in a common log scale. With that said, let's go. The average distance quickly converges to 10. What keeps the average from converging in a dampened oscillatory manner, as would be expected theoretically, is the presence of the zeros at the end. As the amount of digits increases, the effect of those end zeros decreases rapidly, and that explains the quick convergence. A polymer science enthusiast like myself might recognize a very similar graph when graphing glass transition temperature over molecular weight. Much like how here the quick convergence is due to these end zeros, there too the quick convergence is because of the decreasing influence of the polymer chain ends as polymer molecular weight increases. The standard deviation of the amount of digits between repeating digits also converges. Instead of converging to 10, it converges to 9.5. We will see what this means after we look at the other way I measured the spread of the distribution. There is another way to measure the average of a distribution. This average, which skews to higher numbers and can be revealing, is called the weight average in polymer science, and uses the formula below. It is a fraction, where on the numerator is the sum of the numbers squared times the frequency, which in this case is always 1, and on the denominator the sum of the number times the frequency. Because squares are more sensitive to slight increases, this average skews to higher values. Unlike the average, this skewness converges to 19. We can see in the values of e that they oscillate above and below the values, as if random. This indicates that the ability of the zeros at the end to artificially lower the results is negated, and we are getting the theoretical oscillating average I was expecting. The other metric that measures spread is called polydispersity. It is used in polymer science to measure the spread of a distribution. It is quite simple. It is the weight average divided by the average. If there is no spread, then the polydispersity index, or PDI, is 1. The greater the PDI, the greater the spread. Quite predictably, the PDI converges to 1.9, which makes sense since the weight average converges to 19 and the average to 10. The only interesting result where pi and e are different is the maximum distance between repeating digits. Quite predictably, as the number of digits increase, The maximum number of digits until the digit is repeated increases. While an initial look appears promising, the reality is that this data is of the poorest quality. It is therefore not reliable enough information, and it was time to change gears. For now, we've had no interesting results, so I changed my tactic a little bit. I rearranged my results to give me the frequency at which different valued gaps appear. Honestly, I was expecting a chi-squared curve. Instead, I got an exponential decay. The rate of the decay, seen on the graphs as parameter b, was also basically the same. What is interesting is the fact that this is an exponential decay at all. This means that the distance between repeating digits decreases exponentially as we seek bigger gaps. This indicates a fundamental relationship between the digits of pi and e, which is great clickbait, but also interesting. It's interesting to see how e and pi follow the exact same exponential decay and point to some fundamental truth about e and pi. As you can see from the r squared, this relationship is very strong and clearly indicates an important property of these two numbers. Unfortunately, it also means that there is no way, at least that I found, that we can, if given 500 consecutive digits, find out if they belong to e or pi using the gaps between repeating digits. But wait, that's no way to end a video. That's no fun. Surely the data must be telling me something. Surely there's something I missed. I know. I've been treating pi and e as if they're special. But what if they're not? Back to MATLAB, quickly. I have an idea. Let's try something a little different. Instead of inputting digits of pi and e, let's just put random digits. Let's see if the distances between random repeating digits is any different from the distances between repeating digits of pi and e. If it is not, that indicates some type of pattern, and that's worthy of publishing a real paper in a real peer-reviewed journal after this video. If it is, then we still learn a lot, and we can finally answer the question posed in the beginning of the video. Here are the results for those two random sets, and we can see that the b parameter is very similar to the b parameter for both pi and e. Here are 4 more trials, and we can see a pattern emerge. Although the b parameter is similar, it is different, and excitingly, it is different enough to be statistically significant. Here are all the results for select transcendental numbers. On the top row, we see the square roots of 2, 3, and 5. On the bottom row, we see phi, aka the golden ratio, e, and pi. They all follow very similar exponential decreases. This image is a bit cluttered, so let's make things a bit easier to interpret. Since we're just looking at the b parameter, let's just look at this in a series of neat tables I made. We're going to spend a bit of time on this freeze frame, so let me clarify what we're looking at. Each table has 2 columns. The first column refers to the sequence. The second column shows the corresponding b parameter. Let's look at the top left table first. This top left table shows the b parameter of pi, e, and phi. As you can see, the b parameter is very similar in all 3 and indicates no pattern. Let's look at the middle table next. This middle table shows the b parameters of the square root of a few prime numbers. These prime numbers have very similar b parameters to both each other and the numbers in the top left table. I tried several fits, but it simply seems that they seem to stay close to the average of 0.04 without changing over time. This average b parameter of 0.04 seems to be a property of transcendental numbers, since both the square roots of prime numbers and pi, e, and phi stay close to it. If someone is able to derive this instead of just finding it numerically like I did, comment the derivation down below, and I'd be happy to collaborate with you to make a sequel video on this same topic with you for SoME3 next summer. The bottom left table shows the b parameters of the random number sequences. These are the 6 random trials whose graphs were previously shown. Because they're random, there is no pattern between trials. Therefore, we can simply use the average b parameter of these random trials for further analysis. This average b parameter is 0.1174. The last table is really the most important result, and the one that will drive the conclusions. This is really what all the analysis hinges on in the rest of the video. So let's notice the important thing. The important thing is that the transcendental numbers have a distinctly different b parameter than the random numbers. So the question becomes, what does this mean? What does it mean that the b parameter of transcendental numbers is different from the b parameter of random numbers? Well, very interestingly, this indicates a fundamental pattern in the digits that constitute transcendentals, and that these digits are not, as would first appear, random. Although no pattern is known for the transcendental numbers studied, like pi, e, phi, or the square root of primes, I provide evidence to suggest that such a pattern must exist and is a property of transcendental numbers. This suggests that there is an underlying pattern for transcendentals. Moreover, it also suggests that given a certain amount of digits, it is possible to guess the following digits using this distribution. Obviously, the more digits you try to predict, the worse your prediction. But while this is all very, very cool and meritorious of the large part of the video I have given it, none of it actually answers the original question. So let's go back. Given pi or e, how should I know whether this sequence of 500 digits belongs to pi or e? Well, I've been burying the lead, and the answer is quite boring, and that answer is boring because all these transcendentals numbers were, prior to the research I've just done, presumed to be pseudo-random. The answer is that the sequence must appear in both transcendentals at some point, since these transcendentals go on indefinitely. In fact, this sequence, for this very same reason, appears an infinite amount of times in pi, e, and all square roots of primes. But I've just shown that these sequences are not pseudo-random. So does our conclusion still stand that any 500-digit sequence belongs to both pi and e, and in fact to all transcendental numbers which previously seemed pseudo-random? The answer is a very underwhelming yes. See, in the beginning of the problem, I told you that this sequence belonged to either pi or e. See, since they have very similar p parameters, any sequence belonging to one must belong to the other. For pi, e, phi, and all the square roots of prime numbers, not only will the sequence always be present, it will be present an infinite amount of times and with similar frequency due to the similar b parameter. That being said, the frequency at which the sequence will appear will be different between these transcendental numbers and the random numbers. I want to restate this because it really matters. Although a sequence of a finite number of digits will appear in all transcendental numbers, since there are an infinite amount of digits, and in all infinite sequences of random numbers, and will do so an infinite amount of times, what differs is the frequency at which the sequence appears. This frequency is correlated to the distance from the b parameter of random and transcendental numbers. In fact, if you take any two infinite sequences and compare their b parameters to the b parameters of the sequence you want to study, you can then use the rules of probability to determine which infinite sequence this finite sequence likely came from. So, given a sequence, you can, again using the b parameter, find the probability that a certain sequence was created using a randomly generated MATLAB sequence or a transcendental. That's mind-blowing to me because I never even had to test every transcendental to know whether that sequence likely came from there or not. So, as a parting thought, let me say this. Given any large enough number of digits, you can find the distribution of distances between repeating digits, and from there find the b parameter in the exponent of the exponential decay, and from there you can confidently say whether the sequence came from a transcendental number or from a randomly generated MATLAB sequence. And that's pretty cool. Anyway, hope you've enjoyed these observations and this video summarizing this little summer project of mine. This video is part of the third Summer of Math exposition. At first I thought about making a video that explained some nice math about polymer size and different solvents, but then I decided to go for something more original and write my own code and make this video about something completely unique and talk about something that had literally zero relevant search results when I looked it up on Google and YouTube. Hope you've enjoyed it. See you next year. Goodbye.